Welcome back to Real Analysis. Today, we are going to study about the Bolzano-Weierstrass Theorem. We already established that every convergent sequence is bounded. If we are going to look into the converse of this statement, we are going to get every bounded sequence is convergent. This converse, however, is not true. We can look into the subsequence of this bounded sequence and establish that such subsequence is convergent. This is in fact stated as a theorem, the Bolzano-Weierstrass Theorem. The theorem states that every bounded sequence has a convergent subsequence. For us to understand the proof of this theorem, we need to master the following: subsequence, sequence of sets, nested sequence, nested interval property, and squeeze theorem. Let us consider the sequence with terms 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Now, if we are going to omit some of the terms, we omit 1, 3, 5, 7, 9, and all the other odd integers in the sequence, we are going to have 2, 4, 6, 8, and so on. So we will be left with even integers. In fact, the resulting sequence is called as the subsequence of the original one. 2, 4, 6, 8, and the rest of the even integers will comprise a sequence as well. The sequence is a subsequence of the original sequence. So here's the definition. A subsequence of a sequence A sub n is a sequence obtained from A sub n by omitting some of its terms. So remember that the subsequence is a sequence as well, and we obtained it from A sub n, and we just simply omitted some of the terms. A subsequence B sub k of A sub n may be written as A sub n sub k, where n sub k is strictly increasing sequence of positive integers. So we have to take note that we have B sub k now as a notation, and that is with respect to A sub n. And we write B sub k as n sub k, where n sub k is a sequence, not just any other sequence, but strictly increasing sequence. So we just don't simply randomly delete or omit the terms of a sequence to create a subsequence, but we make sure that the subscript of the resulting subsequence is going to be a strictly increasing sequence of positive integers. In the example a while ago, our sequence may be described as A sub n is equal to n. The resulting subsequence is B sub k, which is equal to A sub 2k. Notice that 2k is also a sequence of strictly increasing positive integers. Here is a theorem about subsequence. If A sub n converges to L, then every subsequence of A sub n converges to L. This means that the sequence and its subsequence must have the same limit. The next terminology that we need to be familiar with is sequence of sets. Sequences of sets are similar to sequences of real numbers, with the exception that the terms of the sequence are sets. For sequences of real numbers, we map the set of natural numbers to real numbers. But this time around, for sequences of sets, we map the set of natural numbers to sets. Here are some examples of sequences of sets. Benson, Kumar, and Tompkins showed this example. We have the first sequence, the set containing elements A, B, and C. That's the first term, and that is followed by another set which contains the elements A and B, and that is followed by another set containing the elements C, D, E, and F. So this is going to be the appearance of a sequence of sets. But we can also think of another example wherein the sets are represented by intervals. So for this case, our set will have infinitely many elements because the elements are real numbers. And for the first set, we have the interval with endpoints -1, 1, and this is a closed interval. This is followed by another set which has the endpoints -1/2, 1/2, and the third set is having the endpoints -1/3, 1/3. These are closed intervals and they can be represented by line segments on the real number line. So this is an example of sequence of sets. Now proceed to the next terminology, and this is nested sequence. A sequence of sets I sub n is said to be nested if the set I sub 1 contains or equal to the next set, which is I sub 2, which contains or it is equal to the next set, and so on. Let's go back to the given example. This sequence is nested. I sub 1 contains I sub 2, which in turn contains the next set, which is I sub 3. I sub 1 may be represented by the red line segment with endpoints at -1 and 1, and I sub 2 is the green line segment with endpoints at -1/2, 1/2. The third set is represented by the purple line segment with endpoints at -1/3 and 1/3. The first set contains the second one, which also contains the third one. And of course, obviously, this third set will also contain the fourth set. The pattern will go on infinitely, and this is an example of a nested sequence. Here is an important property of nested sequence. We call this as the nested interval property. If I sub n, where n is an element of the set of natural numbers, is a nested sequence of non-empty closed bounded intervals, then E, which is a set that is equal to the generalized intersection of I sub n, where n is an element of the set of natural numbers, is said to be equal to the set containing x, such that x is an element of I sub n for all n, an element of the set of natural numbers, contains at least one number. This property simply states that the generalized intersection of all the sets in a nested sequence is non-empty. The next statement is about length. So let us focus on the note below. Length of a bounded interval I with endpoints A and B is defined to be the absolute value of the difference of B and A. So this is similar to our common notion of length. So we just simply get the distance between the two endpoints of this interval. Let us go back to the second statement, which states, moreover, if the lengths of these intervals satisfy that the length of I sub n approaches 0 as n approaches infinity, then E contains only one number, as shown in this statement as the set in the nested sequence is getting smaller and smaller. In fact, the length is approaching 0 as n approaches to infinity. We can say that there is only one number in the generalized intersection of the sets. In this example, the length of I sub n approaches 0 as n approaches infinity. And so, intuitively, we can declare that E will contain only one element, and that element is 0. Remember that E is the intersection of all the sets in the nested sequence. Let us now focus on the squeeze theorem. It is named as such because one sequence is like being squeezed by two sequences, And so this middle sequence is going to adapt the property of the other two sequences. Here is the theorem. Suppose the sequence x sub n, the sequence y sub n, and the sequence w sub n are real sequences. That means that the terms of these sequences are real numbers. If x sub n approaches x and y sub n approaches x as n approaches infinity, and if there is n sub 0 an element of the set of natural numbers such that x sub n is less than or equal to w sub n is less than or equal to y sub n for n greater than or equal to n sub 0, then w sub n approaches x as n approaches infinity. In other words, the sequence w sub n is being squeezed by the sequences x sub n and y sub n. And so the limit of the sequence w sub n will also be the same as the limit of the other two sequences. The next statement is if x sub n approaches 0 as n approaches infinity and the sequence y sub n is bounded, then the product of x sub n, y sub n approaches 0 as n approaches infinity. So this simply shows that if we have one sequence which has a limit of 0 and then the other one is bounded, all we have to do is to get the product, and the product approaches 0 as n approaches infinity. Now that we have mastered subsequence, sequence of sets, nested sequence, nested interval property, and squeeze theorem, we are now ready to prove the Bolzano-Weierstrass theorem.